Begin. We're going to be looking at a problem in section 5.2 related to friction. The problem we're looking at is number 71 on page 145. I encourage you before watching this video to attempt to solve the problem on your own. We have a box or a block that has a mass of 5 kilograms. Has a mass of 5 kilograms. A force, a push force, that's why I said P for push. A force is applied, and that magnitude of that force is 40.0 newtons. 40.0 newtons. We see that the box accelerates. The block accelerates with a magnitude of 6.0 meters per second squared. Our first question is to determine what the block's acceleration would be if the surface was frictionless. In other words, neglect friction in this circumstance. What would the acceleration be? So we're asked to find acceleration, but for a different circumstance. In this case, we need to use Newton's second law if we're going to relate a net force acting on an object to its acceleration. In the original case up here, we have a frictional force that's opposing the push force. And that is what is resulting in our acceleration in the x dimension. These are forces in x. Now for A, we're saying if it's a frictionless table, then we neglect this friction force. And so we only have some push. So we have a push to the right. That push to the right generates some acceleration in the direction to the right. That acceleration would be the push divided by the mass of our object that's undergoing that net force. If the push is a 40.0 Newton force to the right and the mass is 5.0 kilograms, then our acceleration should be, on a frictionless surface, 8.0 meters per second squared. That would be our acceleration if there was no frictional force. But there is indeed a frictional force, and that frictional force changes what our acceleration would be. Our acceleration actually is 6.0 meters per second squared. Makes sense that it'd be a smaller acceleration because this force here works against the pushing force. Question B is to find the kinetic frictional force, to find out how large that kinetic frictional force is. We can start again with Newton's second law by saying, all right, again, forces in the x dimension. We're bringing back in the frictional force, or we're allowing it to exist. It's no longer a frictionless table. So we have these two forces, and those two forces are generating some acceleration in the x dimension. If we're trying to find the magnitude of this frictional force, we'll continue resolving this as the frictional force is in the negative direction. That's its orientation, that's its direction. So we'll put negative magnitude of the frictional force. The push is in the positive direction. And we should probably go back to our picture here and say this is positive and this is negative. Our frictional force plus our push force, that generates some acceleration in the x dimension. If we're asked to find for B how large the frictional force is, then I'm going to rearrange this equation so I have frictional force by himself. So I'll put frictional force on the other side, and then I'll put this that would be joining him, I'm going to put him back over here. So these two guys are going to swap positions. So what I'll end up with is the frictional force is equal to the push minus the mass times the acceleration of our object. We know that the push is 40.0 newtons. You know, the mass is 5.0 kilograms, and the acceleration is 6.0 meters per second squared. So we find that our frictional force must be equal to 10 newtons. 10 newtons of force directed in the negative direction, or opposing the push, opposing the motion of the object. So we found that if it was a frictionless table, that it would have an acceleration of 8.0 meters per second squared. It indeed does have some frictional force opposing it, resulting in a smaller acceleration. Using the fact that we know what that smaller acceleration is, and we know what the mass of the block is, and we know what the push on this block must be, we can find what the frictional force is that is opposing the motion of this block. And finally, we're asked to find what would be the coefficient of kinetic friction. We have a block that is moving along a table, so we have kinetic as opposed to static friction. If we know that this is the magnitude of the frictional force, we know generally that we can define, well, the frictional force, static frictional force, is equal to the kinetic frictional force is equal to the kinetic coefficient of friction, or coefficient of kinetic friction, times its normal force. This is the guy we're asked to find. We already know the frictional force. We just found that in part B. That's what this 10 newtons is. That's our frictional force. We're trying to find our coefficient of kinetic friction. So we need to find what the normal force is. We know that if we rearrange this equation, we can solve for the coefficient of kinetic friction in this manner by dividing by the normal force. So we know this guy, but we don't know what the normal force is. To find the normal force, we'll use Newton's second law again. If we need to find a force, then we can at least start with Newton's second law. The normal force is a force that acts in the y dimension. So we'll look at what are the forces acting in the y dimension. We know we have the normal force that the table is putting on the block, but we also have the weight of the block itself. And that equals the mass times the acceleration of the block in the y dimension. The normal force is oriented upwards, or in the positive direction. The weight is in the negative direction. We are not accelerating in the up and down or y dimension, so our mass times our acceleration is 0, because mass times a 0 acceleration is 0. From here we can conclude that the normal force is equal to the weight. So this is what we're going to put right back up here, right back into our equation for the normal force. Taking one step back right before we do that, we need to say, well, since the normal force is the same as the weight, how do we quantify weight? Mass times gravity. The mass of our object times the gravitational field that it's in. So now I can rewrite this equation up here as the frictional force divided by mg. My frictional force is 10 newtons divided by my mass of 5.0 kilograms times the gravitational field I'm in, 9.80 newtons per 1 kilogram. I find that my coefficient of kinetic friction is 0.20. Remember, that does not have units because here in the denominator we have kilograms times Newton per kilogram, so just newtons, which makes sense because this represents everything here represents the normal force, should be represented in newtons. Our numerator is 10 newtons of frictional force, and so our ending up coefficient is 0.20. That's our coefficient. That's the mathematical relationship between our normal force and our frictional force. One last thing to wrap this problem up is a free body diagram that maybe we neglected here. So if we wanted to demonstrate the free body diagram that would have been used in order to resolve the forces in the x dimension, and then later to resolve the forces in the y dimension down here, we need to include those forces graphically on a free body diagram. We have one force to the right or in the positive that's pushing this block. We have a force that's opposing, kinetic frictional force, that's not as strong as the push. This is the kinetic frictional force that's opposing the motion. We have the force of the table on the block, that's our normal force. And then we have the gravitational force that's acting on the block, which is our weight. These are the four forces that act on our block as it moves across this table with friction. 2 forces in the y dimension, 2 forces in the x dimension, both pairs opposing each other. All right, thank you.